Thank you, everybody, for joining. We're going to talk about building a data lake on AWS. I'm Ian Myers. I'm a solution architect based in the UK, and I focus on big data and analytics problems that are largest and most complicated customer use cases that we can come up with. And I'm really glad to be able to talk about data lake today because it's one of the things that's just really popping up quite a lot. And I think we need to take some steps to define it and help make it real for our customers. Data lake is one of these sort of terms that's being confused and confounded in ways that cloud and big data have historically. And it's really important for us to deal with something concrete. So our objective today will be to give you an idea of what we see as the data lake challenge and give you some patterns that you can use to try and solve that problem for your customers, internal or external. So once upon a time, and perhaps some of you are still there today, the enterprise data warehouse was the center of the universe. It gave us a lot of benefits that we have taken advantage of for 20, 30 years. Those benefits included things like a self-documenting schema for our data, very concrete and enforced data types so that people couldn't make mistakes and interpret data in the wrong way, normalization rules that helped us have consistency with how we expressed business relationships. It gave us a very common, ubiquitous security model. And then, of course, it was very simple to access with a tool like SQL. And it gave us some interesting capabilities around the transactionality that we worked with our data so that we could entrust it with storing the financial systems records from our transaction processing systems. And these are all really important business attributes that we have to consider when we think about building a data lake and defining a data lake and setting priorities for what a data lake even needs to do. One of the things that an enterprise data warehouse does is it very tightly couples compute and storage. The idea is that you push your business logic into that data warehouse, that you build stored procedures and views that sit right alongside your data, and you scale that environment to meet your business objectives by adding cores and RAM, and you have the storage associated with that being highly scalable, highly available. And that's gone a really long way to solving very complex business problems. But our customers have other requirements. They want to be more agile. They want to be able to work with data that doesn't necessarily fit into a pre-specified schema. They want to use pure in-memory tools. They want to do natural language processing. They have a particular requirement to solve a graph problem. And they struggle to do that with a tool like SQL. And so we need to consider how we've moved forward, and we see that there was the rise of the Hadoop ecosystem. And on AWS, Elastic MapReduce provides us a runtime for that ecosystem that leverages the storage environment on S3 and lets us build highly robust, scalable, and diverse engines that can solve lots of different problems. Now, one of the things that the Hadoop ecosystem and the big data solution to a problem helped us do was to take that tightly coupled compute and storage and break it apart so that we could run lots and lots of compute on a system that was independent of the job that you were trying to accomplish. And so, in some ways, big data technologies have gone a long way towards helping us implement this concept of a data lake. But is it enough to say that our Hadoop environment is our data lake? Well, no, it isn't. We need to do more. And when we think about the benefits of separating out compute and storage, we're able to get a lot more cost efficiency because we're focusing on providing the necessary compute just to fulfill the storage requirements, not having everything glommed in together. We can do really interesting things like independent cost attribution for different pieces of data within the storage environment. Rather than looking at an enterprise data warehouse and saying, well, there's an overall cost for that enterprise data warehouse, we can look at what it costs us to store an individual business unit's data and service their compute requirements. This sort of architecture gives us the ability to choose the right tool to solve a problem at the right time. Running elastic MapReduce clusters with Spark, Presto, Hadoop streaming, HBase. Whatever you require is available on demand, and you choose that tool because it's the right way of expressing a solution to a problem. We also have this really nice ability to increase the durability of our data. We use that term a lot, durability. What does that mean? It means how safe is our data? And how do we provide extremely high durability to our data without doing a lot of operations and managing that on a Hadoop cluster? And we can also move towards this idea that I think Data Lake really tries to achieve, which is a common model for data storage without enforcing any type of access method. So the big data technologies are really a start towards building a data lake. But we need to talk about what are the other things that give us the same kind of benefits that an enterprise data warehouse has delivered for years and go much further than just what we can get from a big data solution. If we compare big data versus an enterprise data warehouse, they're very complementary. And you can expect that your big data environment may be producing data for your enterprise data warehouse. And separating compute and storage gives us some really great benefits, like providing a model on read semantic versus a model on write that we have to use when we want to ingest data into our relational database. Big data solutions give us much better agility. We should be able to ingest data very, very quickly because we don't have to go through an analysis process to pull that data in and make it available to our end users. And if we look at what an enterprise data warehouse was good for, it's really, really good at reporting. It's really good at business intelligence. But as soon as we want to do things like predictions, data science, plus those reporting use cases, we start to get into some very challenging solutions. Also, as many of you I'm sure will have encountered, we typically have to make a concession on the amount of data that we're able to push into our enterprise data warehouse. And with services like Amazon Redshift, with such a disruptive price point, we're able to really start ingesting everything into our enterprise data warehouse. But how far do you go? Would you put all of the network exhaust from your platform as a telecoms operator into Redshift? You might. But there can be other ways of solving problems against gigabit per second sort of data sets that a more decoupled architecture will allow. And we see some other attributes, tend to have very, very tight SLAs on our enterprise data warehouse. And in many cases, that is conceded on a big data platform because it's an experiment within your company, or it's not handling the crown jewels. So we have two systems that are really kind of at odds. And they're both serving great requirements within our businesses, but we've often created another problem, which is the two really can't overlap very well. So do we duplicate our data between an unstructured system and a structured system? Is our enterprise data warehouse populated from our big data environment? And how do we enable these other tools to work against data sets that are in the enterprise data warehouse? And ultimately, we need to synthesize these two domains together. We need to give us the ability to harmonize these two sources. And this is an objective that we'll set for our idea of what a data lake can be. So what does this system do? Well, the big data component, the unstructured data management systems, are doing things like ingesting any type of data at scale and very, very agile, and doing things like massively parallel data cleansing. And we also can move towards this idea of having a data catalog that sits outside of our enterprise data warehouse. When somebody in an Oracle environment does a described table, they get the table comments. That's an extremely useful feature. How do we extend that same experience to all of our data? And that process that we employ should be then used to push data into our more structured environment for things like structured analysis, giving access to analysts, potentially doing more efficient aggregation, although a very common pattern is to pre-aggregate at the store everything forever level. And we still get benefit from implementing structured business rules within our enterprise data warehouse. That's not the end of the story, because there's a huge amount of value that we've captured in our enterprise data warehouse that we may need to use to solve other problems. So exporting out computed aggregates, business rules, and so on, so that we can do things like trend analysis, implement machine learning, and so on. It's quite a nice pattern, and you can see how they can work very well together. And so a data lake really needs to provide us this idea that an enterprise data warehouse is just another projection of our company's core data. But it isn't the only thing that we use to solve a problem. And so the benefits that we've been getting from an enterprise data warehouse have to live in other places as well. So the components that we're going to walk through include base storage capability for data, but crucially also our ability to work with streams. A data lake can't just be a massive pile of data at rest. It also needs to be able to support the idea that things are changing all the time. And our storage and streaming layer needs to give us extremely high durability. And a key design pattern that we recommend to our customers is that that storage tier should store raw data as you captured it in the first place. The moment that you reduce the granularity of the data that you store, you are losing business information. Okay, some data you don't need to store. But as soon as you decide that, in fact, it would have been quite nice to have that, and you've deleted it, you're out of luck. The storage API needs to be able to store any type of data at all and allow us to answer the question when a business user comes to us, we just thought we might introduce this piece of data. So yes, absolutely. We can store that. And in order to have that sort of full take architecture, it needs to deliver low cost. And not just low cost, but potentially low variable cost, where we're able to put data in the right sort of system that gives us the cost profile that that data justifies. On the streaming side, streaming isn't just about pushing data in, which is extremely important, and looking at ways for us to move away from a file-based ingest architecture to a stream-based one. And we'll talk about why that might matter in a little while. But also the ability to turn around and say, well, what if I wanted to consume a piece of data from my data lake as a stream? What would that look like? Because that's quite neat. If every time a piece of data changed, I was able just to consume that and have extremely low latency, that can offer some really interesting business solutions and really enable new ideas to be fulfilled. The next component of a data lake that we would ask you to consider is that a data lake is more than just storage. It is not just a pile of data, but it also has this ability to document itself, that it can enable data discovery, and that it can facilitate our end users being more productive with the data. So we need a data catalog, the metadata lake, if you will. And what this is going to do is it's going to give us summary statistics about our data. It'll do things like classification. A really simple problem that we need to solve with our big data systems. Show me all my customer data. Right? How do you do that? It's actually really hard. And then on the other side, search is increasingly important to our customers who need to not just be able to say, I've got a very prescribed way that I ingest data, I move it into this system, and then I do something with it, and then it comes back out again. But I need to be able to just discover patterns in my data, see where data is related, and expand that picture that says, actually, I didn't think that this data source actually had any customer data in it, but it does. And search can enable us to find that. And it's a really important component of our data lake strategy. The next thing we need to consider is what I'm going to call entitlements. Entitlements isn't just security, but it includes security as well as things like authorization, regionalization, chargeback, quotas, masking, all of the things that you may need to implement to be compliant with your business, the contracts that you've signed, and so on. Customers that use S3 can store any type of data, but in many cases, they're going to end up with ubiquitous access or no access at all. And so we need to consider that problem fully, and we're going to give you some patterns that you can consider implementing depending on what your requirements are. And then lastly, we need an API and a user interface that exposes this environment to the outside world. Now, a data lake is, as you might have guessed, composed of AWS services, and of course, they all have APIs. But gaining access to this environment isn't necessarily as simple as just exposing those AWS APIs to your customers, because you have very complex business rules that you've implemented in your entitlement system, and those absolutely have to be respected. That API is really the way that you implement governance of this system. Because as we all know, human policy-based governance is extremely hard to get right. So let's dive into this. Storage and streams. What's it look like? Well, no great surprise. At Amazon S3, the simple storage service provides a foundation for any data lake we build. And it is absolutely not the case that we would contradict the idea that S3 can become your system of record for all the data that you ingest. Why is that? Well, it's a system designed to allow you to store a virtually unlimited amount of data and do so with a durability design of 11 nines of durability. When we talk about keeping data safe in the durability measure, you can think about 11 nines of durability is if you stored 10,000 objects, in S3, you could theoretically lose one of those in 10 million years. That's what 11 nines means. And even that 11.9's durability, we go to great lengths to CRC check and provide checksums of your data to prevent bit rot and allow us to store data on the magnitude that S3 is built for. When we talk about what data can be ingested into our data lake, S3 is completely open to storing whatever data you want. From a tiny 1-byte data marker, including the functionality of S3 that says, I used to have a piece of data here, but it's actually over there, which we'll use for some interesting lineage problems. We can go up to 5 terabytes of storage, and it's happy to store absolutely anything. S3 isn't a file system. It's object storage, which means that we can access it over HTTP. We can put any type of data in, and it only looks like a file because it has a file name attribute and a MIME type attribute. But the AWS SDKs and client tools allow you to work with file data as though S3 was a very simple file system. And S3 is a regional service. So when you create a data storage environment for your data lake and you choose a region that's appropriate for you, S3 is implemented across all the availability zones in that region. And crucially, the data won't be moved outside that region. And with services like AWS CloudTrail, you can ensure that data is journaled and audited for how it's being used. S3 supports concepts such as access logging, and we'll talk about the identity and access management capabilities to secure this data, to make it extremely secure. And then we can take advantage of things like server-side encryption as well as client-side encryption to make this data ultra-secure and ensure that we only use it for the task at hand. S3 is really a great system for ingesting anything and then helping us manage cost as well. And we've long had the concept of lifecycle integration with Amazon Glacier, a service designed for cold storage, also offering us 11.9s of durability, but with a retrieval time for our objects of between 3 and 5 hours. And now we can also take advantage of a great new feature of S3 called S3 Infrequent Access, S3 IA. IA is a much cheaper option that's still giving us online access to our data at a significantly reduced cost. And S3 IA is a perfect environment to use for data that you almost never access, but if you needed to, you have to know it's available. And one of the great benefits we can take advantage of this storage system is that S3 will manage this tiering for you. S3 Lifecycle integration allows you to write a policy that says, after a certain period of time, move my data to S3 IA. After a further period of time, move my data to Glacier. And after yet another period of time, delete it entirely, if that's your requirement. And so we can really look at our data that comes into our environment and say, well, what is the right cost profile for our data? And make sure you target that environment. So what is this data, and how do we store it? Well, consider when you use S3 as a foundation for your data lake that not all file formats are created equally. You're going to have totally unstructured data. You're going to have some semi-structured data that has variability over time. And you are absolutely going to have very structured data. But across all of those different types of data, we really do want to store a raw, first-mile copy of the data so that we can recover our business and almost replay the business, if you will. You would implement a downstream workflow to do things like standardization of your data, implement data cleansing, and so on, but it is absolutely vital that you consider some structure that allows you to store everything as you received it in the first place, and then build a picture of what happened to it as you go. And as you store that data, you should use a data format that is sympathetic to your data, if you will, rather than turning around and forcing everything into a data format that you kind of decided because it seemed like a good idea or it was trendy or whatever the case may be. But you will want to do things like having a common approach to compression. And you want to pick your compression capabilities so that they allow you to work with the data and do things like transparent decompression, streaming, and so on. And a crucial part of how you store data and what data format you choose is to consider how it will change over time. You know, when you choose to store all your data as Orc or Parquet, you have to consider that that's great for the schema that it implements today. What happens when it changes in the future? And is the format going to be able to deal with that change? So for unstructured data, it's actually very simple. Store the native file format, logs, dump files, whatever. We really do mean store everything. But use a codec that allows you to stream that data and work with it on systems like Hadoop very, very easily. I personally advocate LZO compression just about everywhere because it gives us good compression. It's about 20% bigger than gzip, but it's a streaming codec, and it has client tools on Linux, and it's supported by almost every sort of Hadoop tool that you can imagine. Semi-structured data, this is going to be JSON, XML, whatever the case may be. This is an area where you really need to think about evolvability. So a data format like Avro can be very useful for allowing you to assimilate changes to the schema of the data over time. And an interesting ability is to store within S3 an attribute on a given file that says, well, where is the schema for this piece of data? Where can I go look that up if I needed to? And on the structured side, with the best will in the world, lots and lots and lots of data is CSV. You know, these legacy systems, mainframes, application servers that have been built for years are going to be able to generate CSV. It's a very common interface format. And this is an area where you may say actually using Parquet or Orc does make sense because it has a lot of the same attributes of CSV, but it gives us massive, massive compression. But be very careful on selecting one of those data formats because you may find that you need to work with that CSV data with a tool that doesn't support this year's most hot data format. And you know, we have great experience with Parquet, we have great experience with Orc, but just make sure that it's going to stand the test of time for the sort of tools that you require. The other thing we need to consider for a data lake is where should the data be actually stored? Okay, in S3. We're all on the same page there. But S3 has a very flat key space. And if you ingest 100 terabytes of data into S3 and then decide that you don't really like how it's organized, you have a very big job on your hands to change that. So we absolutely recommend that you spend a lot of time up front thinking about how you lay your data out on S3 to give yourself the most benefits possible. Doing things like naturally taking advantage of the partitioning that your data gives you and using a prefix structure that lends itself to a more intuitive interaction with the data. So what does that mean? Well, you might decide that you have a common way of storing data on S3 that takes the business unit, the application name, the type of data that you're storing, and maybe time as a key component of how you organize data on S3. And once you've made that decision, stick with it and make decisions about how you change it very carefully, because we're going to use this almost as a basis for a metadata catalog. And I'd like to introduce the idea of resource-oriented architecture. Something you can read about on Wikipedia. It's an interesting idea that comes out of the way that we would structure a web API, that we expose resources and then the operations that we can perform against those. So this has some really interesting ideas for how we might lay our data out on S3, organized by system, application, the year, the type of data, and then also considering that we might have tagging and resource markers within our data that facilitate building really interesting integration patterns using S3 as a storage system, and we send around the prefix as a key for working with very complex data in our integration system. On the streaming side, it's a real complement to our storage architecture. We need to have data come in, and we need to have data go out, and we need to be agile and consume that not at the granularity of files only, but of lots of other types of data. Streams matter because there's more and more customer focus on latency between an event occurring and being able to take an action. And an enterprise data warehouse sort of architecture, and many even big data systems would target maybe sort of hourly as a latency that's an objective. But streaming is going to be in the 1 to 2 second range. And building an architecture around streams can help us facilitate these use cases, but buyer beware. They can be a little bit more complicated to operate. And so when we consider how do we integrate streams into our data lake, we need to consider the business value that we receive from having a streaming approach. So Kinesis gives us this great ability to handle streams both inbound and outbound. And with tools like Kinesis Firehose, we can have fully managed delivery of data inbound to S3 automatically. Kinesis gives us that streaming capability to also build real-time analytics systems. And the storage is extremely durable. In a similar way to S3, the shards within Kinesis are implemented across multiple availability zones. They give us very high durability, and we can have as many consumers of that data as we require. So the archive and ingestion sort of use case that Kinesis Firehose enables can be complemented with things like sliding window analysis using Spark streaming, automatically loading data into our enterprise data warehouse in the form of Redshift, and also building sophisticated event processing systems. This interacts with our object store in a slightly subtle way. Our analytics applications, of course, are going to be reading and writing file data, but we also have the ability to move away from files. At source, take a file and just stream that onto Kinesis. That gives us a great benefit. On our application tier, we can throw the file away. We don't run out of disk anymore because we've made every single event durable on that stream. Those analytics applications are going to be reading and writing from streams, but we can also implement the idea that we want to replay history of our data lake by having a component that takes a specification for a piece of data on S3 and squirts it up into Kinesis so that our applications can reconsume that. So when you build these type of systems, you need to consider, well, what does a streaming replay look like? How would I detect that an event was being replayed? And what would the business rules be in my application that I'd need to change? And then certainly where you're using streaming for inbound data storage, we push that onto S3 for long-term archival. Moving on in the components of a data lake, let's talk about catalog and search. So the catalog is really about giving us an aggregate picture of the data we have on S3. It gives us the ability to define new metadata characteristics, define things like ownership of data, not in terms of the owner of an object on S3, but a much more abstract sense of ownership. It gives us the ability to think about things like lineage. I ingested a piece of data, then it moved there, then it went somewhere else. We need a component that will do that. And so the data catalog is this abstraction layer that lets us start to consider the idea that we should be able to identify customer data that's more than just a prefix on S3. It's a collection of prefixes. It's multiple regions of S3 even. And this will help us to use our resource-oriented approach to expose this data back to our customers, and it gives us a really nice API for our entitlements system. One of the components of our data catalog is a metadata index. It needs to store information about S3, so this is going to be things like the total size of the objects on S3, the number of objects per prefix, a data classification. This is red data. You have to have a certain entitlement to be able to touch it. When was it last refreshed? Is it versioned? These kind of questions. And a pattern that we would recommend you consider is using Lambda to process S3 events to build this metadata index very easily and store those in DynamoDB. And in fact, we like this pattern so much that one of my colleagues wrote a blog post about it, and I would highly encourage you to read it and use the principles that it implements. You know, this is a totally serverless architecture where we just let it sit there and it maintains all these beautiful metrics about our S3 environment that are a massive improvement on just basic S3 storage. We choose to implement our metadata index in DynamoDB because it has some really great characteristics. It can be a document store, it can be a key value store, it gives us multi-availability zone durability, and it can be scaled on demand. And AWS Lambda is an environment that allows us to implement simple logic without having to run any servers. And in fact, building a metadata index is a fairly trivial problem to solve. I received a new file in S3. I need to make a record of the fact that that object arrived, and then I store its metadata as a summary. I increment counters for size and object count in a prefix and so on. And AWS Lambda is able to scale automatically with the volume of data that's coming into our data lake. On the search side, we want to be able to take all of these different systems that are pushing their data into S3 and give us some standardization about how we interact with that data. And search systems are going to tokenize the contents of our files. It's going to deal with cases in different languages and so on, and also index and match data together. And so we can use services like Cloud Search and our new Elasticsearch service that are extremely simple to use, high durability, high performance, and don't require any operations to scale. So we build on our metadata index by capitalizing on DynamoDB update streams. Pardon me. Update streams give us the ability to consume the changes that are being made to DynamoDB using a streaming interface that we can process with, you guessed it, AWS Lambda. So every time we add a new component to our data lake, it gets registered with our metadata index. That metadata index emits an event that says a file has been added. And then we're able to go and read that file and index it into our search system. And so we end up with a very sophisticated metadata catalog where object created, object deleted is being run through our DynamoDB-based metadata index. And Lambda sits at the heart of maintaining the search index and the metadata index for us. Really nice, simple pattern that allows you then to build whatever attributes you require into DynamoDB, into that metadata index, and take advantage of Cloud Search and Elasticsearch for your search interface. So let's talk about entitlements. Entitlements give us the ability to not just treat this data store as a mass of miscellaneous data, but instead allow us to very finely secure our system. And one thing that I think is an important assertion that you take away is that data lake no longer means completely open access to data. There may be some kinds of data that you're very happy just to store in effectively a pseudo-public context for your business. That's great. That's fine. But in the same way that an enterprise data warehouse gave us a common security model, we need to consider that the data going into our data lake is going to include the crown jewels. And so we can't just leave it open for anybody to access. So identity and access management is a system within AWS that allows us to secure data on S3 and manage users and groups and roles in a very sophisticated fashion. It's based on a policy language, and we're going to look at some of the ways you can use that against your S3 environment to secure S3. The policy language is not just a static point-in-time definition, but it also has this concept of dynamic variable resolution. Here are some of the examples of what you can refer to within an IAM context. They include things like the user ID, the username, how they've authenticated, and so on. So you might say that you use IAM and some of your public open access data, where public means people within your business, they just have to be using a secured transport. Other data is going to be much more subtly secured. And an example of this is, what if I just wanted to let people write data into my data lake, but it had to be qualified as that they own it? You can write a policy that includes the list and the put, uses their AWS username, and that's all they can get at. And that's a nice example of a statically defined and yet dynamic policy for securing our data lake. An IAM federation allows us to extend that definition of who someone is all the way out into our Active Directory environment. So directory services allows you to run an AD connector, and then all of this policy language and all of the security that you're going to build within IAM can be based upon those existing roles in your business. But we do see cases where we need to extend that and build more user-defined security, taking advantage of things like our data classification policy. And this is where the idea of a token vending machine comes in. The token vending machine, and there's a link there for an implementation of a TVM that runs in Beanstalk, that would allow you to implement new business rules for temporary access to your data lake. The token vending machine uses IAM security token service plus other business rules to decide if you have access to something. And the TVM is going to be combined with encryption, whether that's Cloud HSM, the AWS Key Management Service, or just simple server-side encryption, to do things like securing access to our encryption keys. We've encrypted our data, but we need to also control whether or not people even have rights to decrypt data. So we build a customer master key, and that generates customer data keys, and we encrypt our data with that, and then we push it into S3. And we only do that because we had a temporary token that let us do encryption. Now, you might have a policy that says anybody can generate encryption keys, and that's fine. But there could be very sensitive encryption keys that you do need to control access to on the basis of some other metric. So an example of how you would use an entitlement system with a token vending machine to build a very secure data flow is shown here. Your users don't just push data into S3 or consume data from S3, but instead they talk to an API that talks to your token vending machine. It checks your metadata index to determine if the customer is operating in a context where they should be able to access data. They get an STS token that comes back. They encrypt the data with that, the encryption keys that are allowed, and then they're able to push data into S3 because the STS token gave them access to S3 just for that put, which is a really, really nice pattern. And then if we wanted to unwind that for gets, it would work exactly the same way, only that last mile would be a get, where our access to an individual object has been secured with an STS token. And then lastly, we need an API and a user interface that exposes this, because while S3 is the foundation for our data lake, customers can no longer just go and browse all the data in S3. They have to work through our entitlement system. So you may find that when you build your data lake that IAM is adequate for your security model, but as you move further and further towards building things like data classification into your metadata index, this concept will become more and more important. And then we ask the question, well, should we architect our data lake in a similar way that we've built services within AWS, and say that anything that we expose from a user interface perspective has to go through the API that we've built? In either case, the API is going to be extremely important to expose our token vending machine. An API gateway is a fantastic service to enable you to present APIs that do things like have versioning. You can distribute API keys and build an SDK for that automatically. Imagine if you could distribute a data lake SDK to your internal developers. Awesome idea. And you can do things like exposing services through whatever language you're happy implementing and whatever runtime, whether that's Docker or Beanstalk. But you can also use Lambda functions to implement this. And this is a great idea. How do we build a token vending machine in Lambda? It's actually a very straightforward thing to achieve. It also has some really nice features. It does some caching, it does throttling, it does some really useful things that our data lake API will require. I would highly encourage you to consider building that into your environment. So whether you're going to be syndicating the data lake internally or externally, all your API calls are going to go via CloudFront, and then hit the API gateway, which gives us caching, monitoring, and then implements our endpoints on EC2, whatever the case may be. So ultimately, our API and our UI architecture sees that our users fundamentally get access to the API gateway through IAM, or through something like our Active Directory policy. We may implement our user interface in Elastic Beanstalk and drive that with API gateway, but ultimately the token vending machine and Lambda are really working against our metadata index most of the time to give us a token that allows us to access our data lake. So then overall, where have we ended up? A data lake needs to be a foundation of extremely durable storage, the ability to consume that data and archive it through a streaming interface, and crucially includes a metadata index and a workflow which helps us categorize and govern that data that's stored in the data lake. We add to that metadata index with a search index and workflows which enable us to discover new data, and even consider indexing from a search perspective the metadata index so that we can discover what aspects of the metadata index are available. We also need to absolutely focus on a robust set of security controls, governance through technology, not through policy. For many of us who've done enterprise data warehousing projects, you get a great enforcement of policy because of the model on write semantics, but still going around and fighting with people about when they create copies of data and so on is extremely cost ineffective. And so if we can implement controls within our data catalog that dictate when can people create copies of data and how are those copies secured, we get all of the data governance rules built in. And then the API gives us that last mile to ensure that our entitlement system is respected. This isn't something you can leave up to chance. You cannot afford the possibility of data leakage from a system like a data lake because it is everything within your business. And what does that look like? At a very high level, we have a foundation of S3, Kinesis, and Glacier for our storage and streaming. We have a data catalog implemented on DynamoDB and a cloud search or Elasticsearch index providing a search capability, all backed up with AWS Lambda as our data orchestrator for this flow of data through your data lake. And then our entitlement system has at its heart a token vending machine that's built on something like Elastic Beanstalk or the EC2 container service that encapsulates temporary access credentials to data that are fundamentally based upon the information in our metadata index, which gives us the flexibility to define any type of rule we require. Sitting at the top, the API and the UI expose this to your internal users, sits on your intranet. Potentially, you expose this as a service to your customers. And then the only way that our customers are able to access data on this data lake is through temporary credentials that are vended to us by that token vending machine. So thank you very much for your time and attention. I'd like to request, if you could, we would love to hear what you thought about our idea about what a data lake really ought to be. And I would say thank you very much, and I would open the floor for any questions that people have. And thank you very much.